This is our lesson for section 6.5, Simplifying Radical Expressions. Today will be our first day on section 6.5, and we will continue this on our next block day as well. So today we are going to extend on something we've already done before with square roots, but now our radicals will include roots that are cube roots, fourth roots, fifth roots, etc. And so you can see from our PowerPoint, it says for a radical to be in simplest form, you must use the properties of radicals to remove any perfect nth powers and rationalize denominators. You might want your half sheet orange sheet that has all the perfect nth powers handy as you do this, and learn those so that it makes things easier. So a radical expression is simplified when three things are true. First, the radicand contains no perfect nth factors other than 1. 2, the radicand contains no fractions. And 3, no radical appears in the denominator of a fraction. So we're going to look at some examples. We're actually going to start with a square root. We have the square root of 12c to the 6th, d to the 3rd. And now we're going to involve variable expressions. As you look at this, you already know that 12 breaks into a perfect square factor of 4, which I'm going to put under the first radical, and what's left over is 3, which will go under the second radical. C to the 6th is actually a perfect square because the power of 6 is divisible by the index of 2, which is implied, so I'm going to leave C to the 6th under the first radical. D to the 3rd, on the other hand, the power of 3 is not evenly divisible by 2, so we have to break it apart. We want to write the largest power less than 3 that is divisible by the index under the first radical, and so 2 would be divisible by 2. So I'm going to put d squared under the first radical, and then I have one factor of d left over, which will go under the second radical. Now I've taken all the perfect square factors and grouped them as a product under the first radical, and I can take the square root. The square root of 4 is 2. The square root of c to the 6th, 6 divided by 2 is 3. For the square root of d squared, 2 divided by 2 is 1, so that'd be just d. And then we have the square root of 3d left over. You might be wondering about absolute value bars, as we've talked to them last time we were together. When you take an even root of an even power that results in an odd power, we typically want to insert absolute value bars around those unknowns. I do want to point out that in the original problem, if you have a variable raised to an odd power, for this variable to be defined, it actually implies that it would have to be positive for the radicand to be defined. So for instance, in our problem, d raised to the 3rd, the assumption has to be if this radical is defined as a real number, then d has to be positive. Otherwise, a negative value raised to the 3rd power would result in a negative radicand, and that's no good with even roots. So the only radical I'm really worried about is the c to the 6th, because we don't know whether c is positive or negative. And so when we take the square root, an even root of c to the 6th, an even power, and it resulted in an odd power, 3, that's where we do need to insert the absolute value bars. Again, I'm trying to get you to understand that. Do your best to trying to insert them, but I'm not going to be taking off for that. Just do the best you can. All right, let's move down to our next problem. This time we're going to deal with cube roots. So we have the cube root of 125 m to the 30th, p to the 20th. Now, 125, if you look at your perfect cubes, happens to be a perfect cube. So I'm going to leave that entire quantity under the first radical. It's actually 5 cubed. M to the 30th is actually a perfect cube because the power of 30 is evenly divisible by 3, but p to the 18th is not, or p to the 20th is not. So 20 is not evenly divisible by 3, 19 would not, but 18 would be. So I'm going to break p to the 20th into p to the 18th, and then what has to be left over would be p to the second, so that the product would still be p to the 20th. And now we can take the cube root. So the cube root of 125 would be 5. The cube root of m to the 30th, 30 divided by 3 is 10. The cube root of p to the 18th, 18 divided by 3 is 6. No absolute value bars needed when it's an odd root. And then we have what's left over, which is the cube root of p to the second. And of course, as long as that power is less than the index, then you should have pulled out the largest factor. Let's look at the next one. So this time we have the fourth root of 32x to the 5th, y to the 4th. 32 is not a perfect fourth. You might want to look at your perfect fourths. And I'm trying to think of numbers that I can divide into 32 that are perfect fourths. And as I look at my perfect fourths, I see that 2 to the 4th is 16, and 16 goes evenly into 32. So I'm going to put 16 under the first radical, and the leftover factor is 2. X to the 5th, 5 is not evenly divisible by 4. The largest exponent less than 5 divisible by 4 would actually be 4, which means I have to have an extra factor of x left over, which goes in the second radical. Then y to the 4th is obviously a perfect fourth because 4 is divisible by 4. So now I've broken it into the perfect square factors and what's left over. Remember, in the original radicand, the x to the 5th has to imply a positive number for the radicand to be defined, since it's an even root. So the only one we have to worry about absolute value bars with will be the variable y. So when we take the fourth root of 16, you got to be careful not to say 4. The fourth root of 16 is actually 2. We're going to have x. We're going to have y. 4 divided by 4 is 1. We have the leftover, the fourth root of 2x. And then the absolute value bars, I want to put around the variable y because I took the fourth root, an even root, of an even power, 4, which resulted in an odd power, 1. I didn't need it around x because x has to be positive if x to the 5th is going to generate a positive outcome in the original radicand. All right. Let's move down to some fractions where we have to rationalize. So we've got the square root of a to the 9th over the square root of b to the 5th. What I need to do is create a perfect square. B to the 5th is not a perfect square because 5 is not evenly divisible by 2. But if I multiply by just one factor of b to the 1st, that's going to make the denominator become the square root of b to the 6th. And that will be a perfect square. In the numerator, that means I'm going to get a to the 9th under the radical times b. So I've got to think about how I can break up. Hopefully you understand 9 is not evenly divisible by 2, but 8 would be, and the square root of a to the 8th would be a to the 4th, and that would leave me with one extra factor of a that goes along with the factor of b, and then in the denominator, 6 divided by 2 is 3, so that becomes b to the 3rd. And we don't have to worry with any powers here because for our radicands to be positive, both a and b would have to be positive since it's a to the 9th and b to the 5th. All right, let's move down to another one, a fifth root. The fifth root of the fraction 3 over 4y, I first rewrite as the fifth root of 3 divided by the fifth root of 4y. So I have to rationalize the denominator. So that 4 in the denominator, I'm trying to think, can I multiply 4 by any number that creates a perfect fifth? And so as I'm thinking about it, I know 2 to the 5th is 32, and 4 times 8 is 32, so I'm going to choose 8, which means I've got to do that in the numerator. And it's y to the 1st in the denominator, so if I just use y to the 4th, when I multiply, that's going to create y to the 5th. So now when I take the product, my denominator is the fifth root of 32y to the 5th. The numerator, on the other hand, is the fifth root of 24y to the 4th. And as I take a look, when I simplify, the denominator is just going to become 2y. And now we have no radical in the denominator, which was what we were attempting to do. The numerator, 24, does not have any perfect fifths in it, and the power of y is less than the index, so that's all we can do. Let's move down to this one, number 6, the cube root of the fraction 2 divided by 9x. I first rewrite it as the cube root of 2 divided by the cube root of 9x, and I'm trying to create perfect cubes. So I think of my perfect cubes, and 3 cubed is 27, and I know 9 times 3 is 27. So I'm going to multiply the denominator by 3, which means I need to multiply the numerator by 3. And it's x to the 1st, so I need x to the 2nd to create x to the 3rd. So I have to multiply my numerator by that. And so now the denominator, oops. Let me try that again. The denominator will become, oops. The cube root of 27 x to the 3rd, while the numerator becomes the cube root of 6x to the 2nd. Now I'm going to go horizontal here because I didn't leave myself room to go to the next line. But now we can see the denominator will become just 3x. The numerator, on the other hand, we cannot simplify. There are no perfect thirds in 6 or x squared. So we've got the cube root of 6x squared all over 3x. Couple more. Number 7, 2 times the fourth root of 8x cubed y squared times 3 times the fourth root of 2x to the 5th y squared. So we would want to multiply the non-radicals together. The 2 and the 3 give us 6. And then the fourth root, assuming our radicands are positive, which is what we are assuming, 8 times 2 would give us 16. Then we're going to get x to the 8th and y to the 4th. The good news here is that is a perfect fourth. 2 to the 4th is 16. So when we take the 4th root of 16, that is 2. And for x, 8 divided by 4 is 2, so that'd be x squared. And for y, 4 divided by 4 is 1. So we have 6 times the quantity, 2x squared y. As we look in our original problem, the y's were both even powers while the x's were not. So we are going to have to be concerned about the y and the absolute value bars. So I'll change the color here. We would want to insert those absolute value bars around the y. And then the 6 times the 2 means our final answer becomes 12 x squared y, which, again, the y is going to be an absolute value bars. One more problem. All right, last problem. 3 times the cube root of 128 plus 5 times the cube root of 16. I'm going to break up the cube root of 128. Now, this is where that half sheet comes in handy. I'm trying to think of what perfect cube goes into 128. And so as I look at my perfect cubes, 64 times 2 is 128. So I'm going to put 64 in the first radical and the 2 in the second. And that's good. The 16, we know 8 goes into 16, and that's a perfect cube. And that would leave left over 2. So really, we have, if we simplify the cube root of 64, that's going to be 4. And 3 times 4 is 12. So we have 12 times the cube root of 2. And likewise, with the cube root of 8, we know that's 2. So 5 times 2 will give us 10 cube roots of 2. And these are actually like terms because the cube root part is the same. That'd be like 12x and 10x. We can combine like terms, and 12 times the cube root of 2 plus 10 times the cube root of 2 gives us 22 times the cube root of 2. All right, it's going to take a little work. It's going to take a couple days. This is just the first day. I didn't go over every type of problem. So please look in Canvas under section 6.5, the class examples. There are more examples. We will go over problems in class. I am assigning only odds so that you can check your answers. And we'll spend a second day on it on our next block day just to help reinforce some of these. And each problem's a little different, so give it your best shot, and we will go over it again. And I'm probably not going to collect the entire assignment, this and the next block day, until next Monday. So that gives you a little extra time, so don't stress it if there's something you don't understand. Do everything you can. Leave space for those that you have questions about, and we'll answer those questions in class next time I see you. All right, homework, page 419 to 420, 19 to 51 odd.